Is Zahra, and right now I'm presenting our work, and this work was conducted under supervision of Professor Henry Leung in collaboration with Baker Hughes company. Okay, so this is the agenda, and I will go through each one. So the first thing that I want to say is that what is pipeline and why pipeline safety is important. The pipelines are transporting oil and gas, which is the vital resources for our daily lives for long distances, and they are prone to so many kinds of defects. It can be crack, it can be corrosion, or a metal loss. And also, if we don't have the regular inspection of them, it can lead to environmental and economic risks. That's why the regular inspection is really important, and we have the inline inspection, which is non-destructive NDE techniques, in order to monitor the pipeline safety. In that technique, they are using pigs. As you can see here, these pigs are going through pipeline without stop functioning the pipeline, and all the sensors are placed in the pig, and then we are getting the data from sensors for investigating the pipeline safety. Among all the NDE techniques, MFL magnetic flux leakage is mostly used technique, and it applies, as you can see here, a strong magnetic field. And whenever there is a defect in pipeline, the magnetic fields, they are going to distort it and leak out the surface. And using the Hall sensors that are located in the pig in 3 directions, axial, radial, and circumferential, we are going to just somehow measure the leakage and also identify the defect characteristics. MFL is valued for its low cost, for somehow finding the defects in high speed, and also it is mostly used inline inspection technique. So our goal is to just identify and accurately identifying the exact shape of pipeline defects using MFL signals. But while using MFL signals, we face some challenges. The challenges are sorted in 4 categories. The first one is noisy and distorted signals. While we are working with MFL signals, they can simply distorted by any magnetic interference or motion effects and factors like that. The other is difficulty in detecting small and weak defects, because they are somehow embedded in noise patterns, so it's really hard to detect them. And the other is blurred or incomplete defect boundaries because of the presence of noise. And the last one is that traditional methods, they miss subtle defect detections, and also they confuse noise pattern with the defect pattern. So the prior works that has been done in this area, I categorize them into 3 sections. The first one is quantification and classification of the MFL signals. They are really good for classification, but still they can't capture the precise boundary and find structural details. The most recent papers that worked on the classification, there is a Swin YP5 and also Cascaded YOLO VIT. The other ones that works on segmentation of the defects, we have 2 categories of CNN-based and also the hybrid models that they incorporate the transformers into the architecture. So for CNN-based, they improve the segmentation, but they still have problems with weak or small defects due to the low signal prominence and also feature sparsity. And for those who use the hybrid architecture, they improve the segmentation quality, but they struggle with noise-prone MFL signals and fragmented defect pattern, which is really important, especially in our case. To overcome all the challenges that I mentioned so far, we propose a new architecture, which is PixTransNet, that there is a hybrid CNN transformer model, and it meant to increase the segmentation quality. The first thing that we do, we integrated the transformer blocks into the architecture in order to capture the long-range dependency and also in order to detect the fragmented patterns. The other thing is cross-attention fusion module that it surpasses the background noise and makes us to detect the small defects and also increase the boundary precision. And also we did the extensive experimental analysis on 33K of MFL images and showed the improvement over the baselines. This is the overall architecture, and it follows the UNet architecture having encoder and decoder. The encoder is based on ResNet 18 backbone. It has 4 main stages, and the transformer block and also the cross attention fusion module, it integrated into the deeper stages, stage 3 and stage 4. And so what is the transformer block? Transformer block is inserted into the deeper stages, and it uses the multi-head self-attention. And you can see that how the self-attention works here. And also it helps us to connect the fragmented defect regions. On the other hand, we have the cross-attention fusion module, and it uses to integrate the local CNN features with the transformer features. And the transformer features, as they have the global knowledge, they act as the query, and the context is provided with the CNN features, which is the local one. And then for loss functions, we use the focal loss and die slice. We use the focal because we have the class imbalance between the defect and non-defect pixels. So this is the data set, the overview of the data set. For data set, we have one MFL image. The MFL image is consisting of 3 channels, axial, radial, and circumferential, and we consider all 3 channels as the input for model. Then for each sample, we have one corresponding laser image. The laser image shows the exact defect pattern and defect shape that we want to predict. So we extract the binary mask out of that, and this binary mask acts as ground truth for our model, supervised segmentation model. And the pre-processing includes the normalization, and for data augmentation, we use the random cropping. For result, this is the first result that I wanted to share with you, and this shows the performance of our model comparing the existing baseline. For baseline, the first 3 baseline are based on the CNN, and the last 2, they are the hybrid models, and mostly the encoder is consists of transformers. And if you compare the results for the matrix that we provided, you can see that our model is working better comparing to the rest. But if you go deeper into the results, you can see that we have significant increase in recall, and also we have drop in precision. Among our deep analysis that we had for the data, we understood that we have to tolerate that trade-off, because we want to have the precise defect boundaries, and the somehow predicting the precise defect boundary is really important for us. And based on the nature of the data set that we have, that this is fragmented and this is discontinuous. So that's why we have to tolerate the trade-off that we can see for the precision and recall. To further support our statement, we added 2 other metrics, the Hausdorff metric and average surface distance. These are the metrics for somehow comparing the boundaries of the predicted ones with the ground truth, and you can see that we get the lowest one, which is desirable values, because the lower it is, the better the model performs. So this is the visualization of the performance. The first column is the prediction of our model, and the rest, the second one is for UNet model, the third one is for Swin UNet R, and the third one is for segformer. The fourth one is for segformer. The red boxes that I highlighted, these are the areas that our model can detect while the others can't. And you can see that our model is really good at detecting the small defects. This is the input and this is the ground truth, which overlaid on the laser image. And also our model can find the whole defect pattern, which is really important for us. And also whenever we have the subtle signals like the one that you can see here, the model can detect the defects. Another experiment that we done on our model is the ablation study of that in order to know the contribution of each part, each component of our study. And we did the ablation on the cross-attention module on changing the transformer depth and also injecting the transformer into the stage 2, which is the earlier stage. And you can see that the setting that we have right now, it means that having transformer at the stages 3 and 4 with depth of 6, that would be the best performing setup for our model. In order to just show and visualize the cross-attention impact on the output, we just show the activation maps of the encoder. The first column is our model with enabling the cross-attention module. You can see that the attention is so focused and it is focused on the defect area, which is the desired behavior. And the last column is a model without cross-attention module. And by simply adding the local and global features, and you can see that the attention is somehow so sparse, and it is literally showing attention to all over the sample. And the last thing that we did, we provided the threshold analysis and also providing the precision recall curve. And in the precision recall curve, it is obvious that our model is working better in all thresholds comparing the existing baselines. So to conclude the work, we propose PixTransNet. It achieves the significant improvement in recall and also increase other metrics. But still, we have work to do about it, about the future directions. First thing that we should address is the noise nature that it exists in our dataset, and the other is reducing the domain discrepancies between the MFL and laser one that we are using right now. So that's all for my presentation. Thank you all, and I appreciate your attention.